This is the recording of the tutorial Colourful Connections Pigment Provenance Research in Archaeometry. This is for the Young Researchers in Archaeometry Workshop 2022. My name is Alexandra Rodler. I work at the Austrian Academy of Sciences and the University of Vienna, and I will guide you through ancient pigment research and some of the questions and also some of the approaches that we're using. So first of all, what you see here is an overview of a couple of recent publications and also the pigment compendium. This is the dictionary for us polychromy researchers. And then there is the publication by Ruth Siddall, which gives a really nice overview of mineral pigments in archaeology. I highly recommend this for a start to look into this. And a recent series of papers on mortars, plasters, and also pigments, research and questions, as well as sampling criteria. So mineral pigments, they're divided in several subgroups. First, we're talking about earth pigments or ochres. They're used widely in art and for decoration since the dawn of humankind, and they're divided after major elements such as iron, manganese, cobalt, or also by the hue of the pigments. So it would be red, yellow, black, white, green, blue, and purple. Earth pigments are a mixture of various minerals, together with something like quartz, for example. There's clay usually present, also carbonates, and they were also likely mixed for painting then, depending on what time and context they were used in. Earth pigments can be found in surface outcrops near metal ore deposits, for example. They're often a result of acid rock weathering or also mine drainage. They're rather soft and brittle materials, but we'll come to this again in a moment. So here you see pictures of, for example, the Hampstead Heath near London. This is a picture by Ruth Siddall that shows an earth pigment outcrop from acid rock weathering here in forest or along a river bed probably. And then the picture below is from the early futures ochre archive by Heidi Gustafsson. It's an artist, researcher that is collecting earth pigments in the natural surrounding where she's working, and she's also getting earth pigments sent from other places to build a collection. So you can see here someone just digging into the material, so you can see how soft this can be. This is probably also slightly moist. And what you see here are examples for wall painting fragments below from Noricum, which is approximately present-day Austria. These wall painting fragments are largely painted with ochre. Mostly here you can see purple, some light pink, also a little bit of red. So these are all different types of ochre pigments. And then the upper one to the side, these are earth pigment lumps and pieces that were excavated at a pigment production facility on Kos. It's late Hellenistic and was part of the ancient city of Kos, so it was found close to the Agora. And you can see here different red earth pigments and also yellow earth pigments. Importantly, the yellow earth pigments can also be transformed with heat to the red earth pigments, as could also be observed on walls after burn, for example, after fire. Then next, I'd like to introduce other mineral pigments, the minerals and artificial materials. So they are natural occurring, but not so commonly available as ochre. And different hues including are also red, yellow, green, as well as purple and blue. And they can lose the intensity slightly when powdered, which is also why some of them were not so frequently used. And then very early on, synthetic analogues to naturally occurring minerals were made by humans. So this is, for example, Egyptian blue, or Egyptian green, which was used from around 3000 BCE. The first evidence is from Egypt, hence also the name, but it was soon also used in Greece and across the Mediterranean a little bit later. And then Han blue and Han purple were in use from approximately the 3rd century BCE. So here, the upper part, you can see examples for Egyptian blue, Han purple. that were synthesized by Berke and published in 2007. So for Egyptian blue, for example, the coloring agent in it is copper, and then was mixed together with sand, some quartz sand, which was probably also rich in limestone, or limestone was added separately. And then flux was added, and all of this was heated to roughly 950 to 1000 degrees Celsius, and then fused together. We'll look at this a little bit later again, but it's one of the key pigments that connect metalworking, glassworking, as well as the pigment industry, and that have been used for a rather long time and across a wide area. Here in the bottom you also see a morsa with a cinnabar ground finely. So this is also a mineral that occurs not so frequently, but still there are a couple of outcrops that have also been used, for example, by the Romans, or also before already during the Neolithic, where rocks, sometimes very pure, could be mined, could be taken from the mines and then just be crushed, like here in a mortar or something similar. So it's also a very fine powder that is generated like that. It can be used for then painting or also other purposes, of course. So with the next couple of slides, I just want to give you a brief overview of some pigment use contexts, some settings where a lot of paint was found or also just very little, and we'll continue from there on how also ancient polychromy research was initiated, or the first important steps. So here what you see is, for example, a twin burial in Krems-Wartberg in Austria. It's estimated to 40 to 30,000 years ago. Both of them were buried in thick layers of red paint. And then in the middle here you see a mummy with a beautiful mummy portrait. That's part of the collection of the Met. And then when you go to the side, you see, for example, from outside the Valley of the Kings in Egypt, and then also from the inside. And again, the beautiful paint along the walls and on the ceiling in various colors. And a little bit below, from the outside, at Tranquinia and Etruria. Also graves, and then from the inside, the paintings, again on the walls and the ceilings, also very beautiful and colorful. And here, one of the very early examples, so ancient cave art paintings from France. Again, the use of various kinds of paint, of various colors and hues, mostly earth pigments, but also some minerals were used early on. And here you see wall paintings at Pompeii. Also, again, beautiful range of different types of pigments that were used to paint the whole walls and up also to the ceilings, as you probably know from some other sites. And now here is a very interesting case. So this is a marble sculpture of Artemis, also from Pompeii. It's dated to about the 1st century BC to the 1st century AD, and is housed at the Archaeological Museum in Napoli at the moment. And to the side you see a reconstruction from 2018 that's housed at the Winkelmann Museum, was part of the Gods in Color exhibition. And what you see here are some smaller pictures of paint remains, so mostly here in yellow, of the diadem, and then the left arm, and then also the color remains on the dress. So these were some of the early indications, or what triggered the early research into ancient polychromy, and that perhaps marble sculptures of the classical period were not just white, as was suggested often later on, but might have been painted partially or completely. So just to give a brief overview, some of these traces of color can be found with just bare eyes or with microscope and good lighting, of course. But some other traces can also be found in different ways. So what you see here are some non-destructive in situ methods, such as the imaging analysis, I'll explain in a moment, but also mineralogical analysis and chemical analysis by XRF. So what you see here are instruments that can analyze the composition of the paint without destroying it. And the two examples that you see are mummy portraits, so it's very clear that they were painted, there was a lot of paint there. But these instruments, these techniques can also be used where there's just very little material left. What is even better in that regard, though, is the imaging analysis that you can see here with the visible induced luminescence imaging that was developed by Anevlavi and published in 2009. This was developed at the British Museum. And what you see in the upper part is the foot of an Amazon marble sculpture. And you can see clearly that there are some carvings that should indicate there is a sandal. But what is not visible, what you can see in the image below, the VIL image below, is that there was the use of Egyptian blue. So there was with this Egyptian blue, there was a sandal painted on the foot that cannot be seen anymore today, because most of the paint was lost, perhaps even removed. But here, with the VIL image, we can clearly see there were traces, or there still are traces of Egyptian blue, and this was likely painted on this foot. So this is an excellent technique for detecting very, very faint traces of color. And here, in the case of Egyptian blue, the fluorescence is because of the properties of the copper that is part of the Egyptian blue. But this principle also works for some other pigments as well. For example, for the organic madder lake that also was used sometimes for painting sculptures. Now, another approach for pigment analysis is also a quantitative chemical analysis. For example, element and isotope analysis by mass spectrometry. You can also use microprobe analysis, of course. And when it comes to elements and isotope analysis by mass spectrometry, which is also what I use in my research, the questions are to detect the provenance of the raw materials that were used for producing the pigments that we then see on ancient art. And the questions we can ask is where material came from, how it was processed, and with an exclusion method, we rather say where it's not from, and then with the context of the material, derive to a point where we can say this might have been a source area. So we look at the chemicals, the chemical composition, the trace elements. Major elements also tell us what type of pigment it is, and the trace elements can then tell us a little bit about the potential provenance. And we can compare to the geology of different source areas. So just very briefly, what are isotopes? So isotopes are atoms with the same number of protons and electrons, but they're distinct numbers of neutrons. So the number of neutrons is also what we then call the atomic mass. Or rather, the different number of the neutrons then also makes for a different atomic mass. Here you see an example for carbon isotopes. So to the left is the carbon-12, which has a mass number of 12 and atomic number of 6. And then to the right is carbon-13, which has the mass number 13, atomic number 6. This difference in atomic mass can mean that there is a different reaction between the isotopes. And this we can then later use to look at different processes that are recorded and preserved in the materials that we analyze. And what you see here, I used apples just as examples, where the different amounts of neutrons should be symbolized here with just the seeds of apples inside that we don't know before. We just see the apple from the outside. But the difference in neutrons, that's what matters for isotope geochemistry. And then, of course, also all the way to the right side is a bit of an older apple. So there is also decay chains that are involved. So like from parent to daughter isotopes. These changes can also be relevant for how we evaluate the samples that we have and how we evaluate the potential provenance of pigments, for example. And all the way below, again with apples, you can see heaps and just big piles of apples, and then we sort them in likewise bags of apples and then give them names. This is also what we do with isotopes, but I'll come to this in a moment. So what you see here is we're taking up from the apples. So we're going to these are schematics for different approaches in mass spectrometry. So the one below is, for example, for TIMS, where from the source, That's where our samples are. So they are processed, as you can see here in this yellow drawing, where the samples pass through some sort of gooey material, and the elements of interest are collected below, whereas all the rest that's part of a sample will be retained, or the other way around. And then in this way we isolate, for example, lead, and then the samples go into the source, they're ionized and they send along with an ion beam through a magnet, and this magnet then separates the different masses of isotopes, which are then later in ion detectors collected, and then we can calculate how many of which isotope were sent through and included in this sample. And a similar approach applies also to multi-collector ICP-MS, which is the sketch below, above. It's just in liquid form there, and some slightly different intermediate stages are included as part of the instrument. But the results are the same. We'll get out in a detector the different masses of the element of interest, the different isotope masses, so we can calculate how the ratios of different isotopes to each other are. And this can then be used to infer where, for example, raw materials came from when comparing to reference material that we know of already. So for my presentation, I will focus mostly on lead isotopes. This is what I use for my research, and it was quite commonly used in archaeometry. So an important aspect is that technological processes are not expected to fractionate lead isotopes between the raw material and the finished product. So there have been some examinations of ancient glass and clays, for example, and lead occurrences that were close by and assumed to have been used. There were also experiments to test how the lead isotope composition is similar, or what the difference will be between galena, so naturally occurring lead minerals, and then pigments produced from this galena. And then there's of course also a large body of lead isotope reference databases available that then can be compared to. So in this way we can find out where the pigment raw materials potentially came from. So we can compare to different mining areas and different regions around the Mediterranean, for example. And what you can see here in the middle is the decay chain of lead, of the lead isotope system. So lead 204 would be the stable one, and then 206, 207, and 208 are products of different decay chains. And there it depends on how much of the burned nuclide was present, and how long it had already to decay, and the different relationships of these three radiogenic isotopes, so lead 206, 207, 208, over lead 204, can give us an indication of what area the raw materials might have come from. So how young or how old the rocks from this area were or are can help us understand how trade interactions were happening in the human past. Important here to note though, like I mentioned already before, the best approach we can use here is to exclude less likely source areas. So it's difficult to just pinpoint exactly at one mining area or one mine even, but it's possible to say, okay, this material was probably not from the Iberian Peninsula, or this material was not from Turkey, for example. So in this way we can slowly approach to where it might have come from, what remains afterwards. And this is, of course, needs to be set in the context of the where the material was found, so the cultural context of the marble sculpture that was painted and the paint that was then analyzed later on. That needs to be the deciding factor, and also what we can exclude or propose as source area. Okay, so next I would like to show you a couple of examples of some previous research on raw material provenance, like that I mentioned a couple of times now. We look at this now with a few examples, and then also the organization of production. So here with examples for the Ishtar gate, so the colored glazes that you can see here to the right, and then right below the text and Egyptian blue palettes. We'll look at these as well. So first, the New Babylonian Ishtar gate and the processional way. Here you can see a reconstruction in the Pergamon Museum in Berlin. And to the side are 3 examples that are part of the collection of the New Carlsberg Glyptothek in Copenhagen, Denmark. So it is estimated that over the whole Ishtar gate, there were around 575 bolts and then these dragon creatures, the uppermost one of the 3 panels. And on a processional way, there were around 120 lions that were walking away from the gate, so towards people coming to the gate and visiting. These were excavated by Colourful and published in 1914. And it has always been assumed that there were several building phases to construct this giant gate and processional way and all the glazes that were used to them. So to look at this organization of production of these glazes, we took several yellow, green and blue glazes here from the different panels. We tried to take them very close to the animal where there was no indication of recent working or reconstruction of the glazes. And then there was trace element analysis done as well as lead isotope analysis, and I'll show you the results in a moment. So what you see here are lead isotope piplots. We'll see them again later, I'll just explain them now already. So on the x-axis is the 206/204 lead isotope ratio. And on the y-axis are on top the 208/204 and below the 207/204 lead isotope ratios. The samples are here with the blue and greenish, green and yellow stars. And then the triangles are largely from areas where the raw materials might have come from. So they plotted the best, and in statistical evaluation they were the closest match in a way of excluding other source areas that have least likely been used. So we can see here for green, for the green glazes, it was most likely copper ores that were used to produce as colorant for the glazes, to produce these glazed tiles. And for the yellow, it was likely the antimony ores or mixed antimony leads and copper ores. And the most likely source area for both the copper and then this antimony lead copper ores we proposed was from the Taurus Mountains in Turkey. In the lead isotope piplots, you can also see here in this yellow greenish ellipses, to make it a little bit easier visible. So the green and the yellow, they plot quite closely together, so they might have come from similar source areas, which we propose for the Taurus Mountains, Turkey. And here also in red, this red point on the map for Babylon. So this is also to visualize the distance that had to be overcome to transport the raw materials to the place where they were used for the glazes. And now to the blue glazes that were found on both the lion panel but also the other 2 panels from the Ishtar gate. So they were likely mixed copper, cobalt, nickel ores, and we proposed that the raw materials were potentially from the Pontic Mountains in Turkey. And they were consistent across these 3 different panels. So you can see here to the side again lead isotope piplots. The 3 blue stars are for the lead isotope ratios of the blue glazes that were analyzed and were taken from the 3 different panels. So they have a little bit more of a spread, but they nicely follow the Pontic Mountains lead isotope field here. So we proposed that there was actually similar material that was used. So with this, we proposed that there was likely a continued supply of raw materials for both the green, the yellow, and the blue glazes over the duration of the construction of the Ishtar gate and the processional way. Now with this, the next example I would like to discuss with you is Egyptian blue. That's, here you can see a slag with fused Egyptian blue pellets from a Egyptian blue production facility at Memphis in Egypt that dates to around the 3rd century BC to AD. And this particular artifact was dated to the 1st century BC. So when looking at this Egyptian blue, we investigate both the technology of production, the provenance, and also the organization of production. And I'll come to this with a few examples. So just first, to give you an overview, Egyptian blue is the copper compound, again, is what gives the color. And that's also what we can trace, so the provenance of the copper, first and foremost. So this is the earliest known synthetic pigment, and uses this copper ore or also bronze scrapings, as well as the calcium-rich sand or quartz sand, and then calcium added, and then plant ash as a flux. And was liquefied in crucibles and was used very widely across the Mediterranean, first starting in Egypt, like I mentioned earlier, and then soon coming to Greece, and from there also, or from both places potentially, spreading all across the Mediterranean, specifically during the Roman times. And here in this map of the Mediterranean, you see a couple of places with stars of known production facilities. So a lot of them in Egypt are focused on Bronze Age, and then later on is the workshop at Memphis, and almost contemporary, 1st century BC, is the production in Bay of Naples and at Kos that we know of already. And there was also production at the Ayanis fortress in the 7th century BC. Now here again, you can see the slag that I just showed you before, just a slightly different angle. So the fused Egyptian blue pellets on the slag, and then to the side from the same production facility at Memphis is a terracotta fragment with blue fritz coating on one side. It might have been the inside of a furnace or a sort of container. And the images below are the VRL images that I explained earlier. It's a technique to visualize copper as part of the Egyptian blue. So these were excavated during Petrus excavations at Memphis in 1910 and belonged to the production facility that was likely active between the 3rd century BC and the 3rd century AD. So here you see again the same two artifacts, and then again the lead isotope pipelets as before, with 206 over 204 leads, and then 207 over 204 and 208 over 204. And a range of different lead isotope fields from areas or ore deposits that we can compare to. So different copper ore deposits. And then in yellow, the Egyptian blue samples from these two artifacts that plot very closely together, so they almost overlap here, which also indicates that the copper for producing Egyptian blue likely came from a similar source area. So we compare a couple of different ones here now. So first here in orange are Italian copper ore deposits. First for the Eastern Alps, and then in grey for Tuscany, and then also here in green for deposits, copper ore deposits of the Araba Peninsula at Timna and Fainan, for example, also Wadi Amram. And last here in purple, Greek or Aegean copper ore deposits that plot quite nicely with the two samples from Memphis. So with this, we propose that Aegean copper ore was most likely used at Memphis for producing Egyptian blue at this Egyptian blue production facility in Memphis. Then another example I wanted to show you are Etruscan antefixes that you can see here. First with the visible light pictures, and then the VRL, so the visible induced luminescence imaging, where you can see the luminescence of the Egyptian blue in various parts of the antefixes. So these roof ornaments, you can see here a fragment of a drawing of a roof where they were likely mounted. So three of them belong to the same building, and two might have been made with the same mold. At least they have a very similar appearance. So there might have been the same workshop producing these different antefixes and then using different paints to also paint them. It might have also been different workshops involved, of course, and they dated to the classical to early Hellenistic periods and were found in Cerveteri in Italy. So the samples were taken where you can see these blue points. We started with the first one on top, and here to the side you see again lead isotope biplots with the specific sample with the black, slightly larger star. And you can see how it plots with here in this example, again with Aegean copper deposits. Then the next example, so the middle antefix plots quite well with copper deposits from Balkan, from Ibuna, for example. And the last one, the Means, has a copper isotope composition that is very similar to Iberian copper deposits at Catalonia, for example. So now when we look at this, at these different antefixes that were likely used for the same building and perhaps produced at the same workshop or in the same context of workshops, we can see that copper from lots of different source areas was likely used to produce the Egyptian blue that was then used for painting these artifacts. So there was likely Iberian copper used, but also a Baltic copper and Aegean copper. So this suggests that there was a rather complex trade network of this particular pigment. Now here in this map you see the artifacts, of course, but you also see again the different Egyptian blue production workshops. And what is quite evident, even though this pigment was used quite widely across the Mediterranean, there are just very, very few Egyptian blue production workshops that we know of. So the production of this pigment might have been as widespread as the use of the color, but it could also have been fairly centralized and then pulling in resources from lots of different areas, probably as part of the copper trade network or interconnected with it. And here on this slide, you see a couple of examples of Egyptian blue, now just single pellets compared to before it was fused with this rather large slag. So here you see singular, some in the middle there are 3 pellets fused, it's quite common actually, but the others are rather singular and they're rather large when you look at them, or there's a difference between them. One can hold in my hand, another one is rather big, it's rather the size of a palm, and all of these are from the Roman periphery from Noricum, which is overlapping with present-day Austria. You can see here in the map, so the blue signifies the borders of Noricum, whereas the red would be present-day Austria. And now a way of investigating this and looking at these different materials that were found at different sites, different Roman sites across Noricum, is just to look at the different composition, both in mineralogy, but also in chemical composition, and then again lead isotope composition. And with this, there's again the idea of looking at whether all of these materials were imported from maybe one or at least a few rather centralized workshops, or whether they were produced rather locally with the knowledge of people present there and using the local resources. So one way of looking at this organization of pigment production and of the pigment industry is also looking at the composition of such samples like Egyptian blue. Here you see microprobe analysis of different fragments. So you see the uppermost are all from Noricum, which is the area that I just showed you, and some of the examples that I just showed you on the previous slide. And the examples from below are from Ostia to the left and from Kakemish in Turkey to the right. What you see here, it's marked in all the different examples with CUP, cup for cuproiavit, which is the mineral that's produced in the course of the Egyptian blue production. It's also a naturally occurring mineral with the same stoichiometry as the Egyptian blue. So this is this darker gray, and then it has usually a little bit of a lighter gray around it. This can of course depend also potentially on the firing temperature or the processing technique. And what you can see here, that there is some slight difference between so the first row, the upper row of the Egyptian blue pellets from Noricum. The first three, starting from the left, are fairly similar. They have a similar internal structure, and the crystals look alike as well, whereas the one to the far right, the FS 212, has a bit of a different composition. So this might indicate that there were different production techniques used. This is not possible to see just when looking at the samples, so we had to do a microprobe analysis to actually visualize and characterize also the internal composition of these samples. And then when you go into the lower row for the example from Italy and also from Turkey, they are again similar, at least the one from Italy is similar to the three similar ones from Noricum, so there might have been also similarity in the production process. And the one from Jakobitsch is also slightly older and a much more pure Egyptian blue. So when I did the XRD analysis for these samples, this was a very high percentage of just the cuproiodite mineral, suggesting that the production was very clean and producing a very high quality product. Important is also that between all these samples, all these 6 samples have the same stoichiometry. So there is actually the product and what it was meant to be for painting walls, for example, would have been the same. So there's just some small scale differences that can potentially tell us a little bit about the production technology and also how this industry worked for producing Egyptian blue, and perhaps also can expand to other pigments in the future. So thanks very much for your attention, and do get in touch if you have any questions.